Right, so we finished last time. We talked about, and I know it was a good while ago, we finished by talking a lot about, or we spent all of last time talking about center of mass, how to calculate where the center of mass is, what the center of mass really is, what it means for the center of mass to have a velocity, and so on. And then we continued talking about momentum. And then we used this notion of center of mass to discuss momentum conservation. And that's really what we got. That's really as far as we got to. We got to the impulse momentum theorem, which was a discussion of the which is a formulation of external impulses changing the momentum of a system. And then we came up with the conclusion that if there are no external impulses, then the change in each individual momentum in the system is the sum of the changes of the individual momentum of the system is zero. So go back and take a look at the notes from last time if you want a quick refresher. And I'm just going to continue on. We have a little bit more to say about momentum, and we're going to continue to use momentum as we proceed in the future, but we're going to use it kind of in a synthesized manner with other concepts. So just as a quick aside, before we kind of change gears, I want to say two things. So first thing to note is that Newton's second law refers to the center of mass, or refers to the acceleration of the center of mass. And you guys probably know that. And the reason why you probably know that is because I wrote subscript Cm next to Newton's second law. So something like F net equals ma Cm. Now, importantly, this m is the total mass of the system, and this Cm, this is the center of mass acceleration of the system. And so that is to say, we can use Newton's second law equally well for single objects, for like a single particle or a single thing, as we can for complicated systems. In particular, we could write for a complicated system, meaning a system composed of multiple objects, we can write the following. Remember, I use capital M to mean the total mass of the system. So we would write F net, which is still the net force on the system, equals the total mass times the center of mass acceleration. And then the center of mass acceleration is, well, we know what that is. It's just two time derivatives of the position of the center of mass. So it's d by dt squared, or d squared by dt squared, and then the center of mass position, m1 r1 plus m2 r2 plus dot dot dot, divided by the total mass. And then we can distribute the derivative, and we're left with m1, the m's cancel out, m1a1 plus m2a2 plus dot dot dot, which is just to say that the ma term, when you're talking about a whole system, can be just broken down into the ma terms on each individual component, or on each individual part or piece of the system, which is just a useful thing to do. If you have a force on a whole system, then you might want to write it in terms of the acceleration on each part of the system. Now, there's just one more discussion to be had before we proceed, which is this discussion of the center of mass frame. Now, this discussion that I wrote out in the lecture notes, so these are not forces. These are, so ma is not a force, right? Ma is what Newton's law says the force is equal to. This is the mass of object 1 times acceleration of object 1. Right. So there's a discussion of the center of mass frame, which I don't really want to talk about it because it's not a great discussion. It's in the lecture notes, but the bottom line is that the example that I give I'll actually just go over it. I'll go over it really, really quick. So this notion of the center of mass frame, and we're actually going to talk about it more today if we get that far. But the notion of the center of mass frame is that, remember when we talked about relative motion, right? You could change different reference frames, and you would get like the velocities that you would measure would be different in different reference frames. And like this is the case where we had Anna like walking on a train, and then the velocity that people observed for her depended on what where they were and how fast they were moving. So just like how we can do that for the case of the rock falling on the windshield, we can always just move into the center of mass frame, which is just choose a reference frame so that you're moving at the same rate that the center of mass of a system is moving. In that case, so choose your reference frame so that you are moving with the center of mass of a system. So this can be useful because when you are in the center of mass frame, the center of mass is stationary, right? Just like how from Anna's perspective, Anna is stationary. This is when Anna was walking on a train. So from the center of mass frame, the center of mass is stationary. And so then you can just, then you know if the center of mass is stationary, that means that the center of mass momentum in that frame, or the momentum of the center of mass, is 0. And so you can use that fact that the center of mass momentum is 0 in that reference frame to simplify problems significantly. Like, for example, if you threw a baseball and then somehow at the top of its arc it exploded, well, figuring out where each half landed would be kind of challenging, because a baseball's a bad example. Like, imagine you chuck a grenade or something and it explodes at the top of its arc. In that case, figuring out where each half landed can be kind of challenging because you'd have to figure out the forces on each part. But if you work in the center of mass frame, the only thing that's changing from the perspective of the only motion that's occurring in the center of mass frame of the grenade is it's going up and then down. It's experiencing acceleration, but its horizontal motion is not there because you're in the center of mass frame. In that case, because the momentum would the center of mass momentum would be 0, one half would have to go equally as far to one side as the other half would go to the other side. This is like the picture here is like you, and I'll just draw a quick picture. And this is what's outlined, by the way, in the lecture notes. Let's say you launch and we're going to model this grenade explosion by like 2 halves connected by a spring. So imagine that this thing's launched at some speed. And then it gets to the top of its arc, and then one half, and then it separates. One half goes one way, the other half goes the other way, and then the center of mass maybe lands here. The question is where do these halves land? And so if you work in the center of mass frame, you'll see that this half goes exactly as far back as this half goes forward. And then from there, you can use that information to figure out, if you know the position of one half, where's the position of the second half, and so on. It's a useful tool, and we'll see better examples of it going forward. But I just wanted to briefly touch on that. There is a quick discussion of this in the LibreText in section 4.3. There's also a discussion of rockets, of like rockets, how rockets work in space, which is also a super useful, or it's also an interesting discussion, which kind of explains how is it the case that a rocket can push itself against nothing, right? A rocket's floating up in space. How can it just start going? What is it pushing off against? The answer is that it's not pushing off against anything. And the explanation then is that the center of mass of the rocket and all of its fuel is always fixed in place. What the rocket does is it ejects fuel out one side, so it gets pushed to the other side in order to keep the center of mass in the same location. Right, so I'm going to change gears now. We're going to continue, we're going to talk a little bit about something kind of separate. This is just to demystify the notion of non-conservative forces, and which will be useful when when you guys get to 9b. And then we're going to hopefully make it all the way through to collisions today, but we'll see. So this next bit, by the way, is a summary of what's in the textbook. This wasn't originally in my lecture notes, but I actually liked the discussion that was added into the discussion, so I've kind of summarized it and talked about it myself here. So if you do want to follow along, the lecture notes will be available after lecture. I'm going to be writing some things down, but also go take a look at section 4.4, I think. Yeah, 4.4 in the LibreText, and we'll be following that along roughly. So we're going to talk about, to begin with, we're going to talk about internal and mechanical energy. So we've already talked about what mechanical energy is. at least from us on a surface level. We haven't, and we've talked about what internal energy is, again, at least on a surface level, but we haven't talked about it in a whole lot of depth. Not depth. So just as a quick reminder, the work energy theorem derived from Newton's second law. And Newton's second law involves the formula involves descriptions of the center of mass. So it's the center of mass acceleration. It's the force applied to the whole system. It's the mass of the total system. So the work energy theorem, really, the variables that are present should actually be written in terms of the variables of a system, which is to say, it should really be viewed as the following. So you would have the change in the kinetic energy. I'm writing it this way, 1/2 capital M, that's the total mass of the system, times the speed of the center of mass of the system. Remember, everything that we did with Newton's second law involved the center of mass of the acceleration of the center of mass. So anytime velocity shows up, it comes from that acceleration, which in turn comes from, which in turn has to be linked to the center of mass. This should be equal to an integral from A to B of the net force dotted into the path that the center of mass takes. All I've done is added subscript cm here, and I've made the little m a capital M in the kinetic energy. So then the question then is what happens if our system, the system that we're talking about, is really just a single object, and that object is made up of trillions of atoms, for example? So the example, the best example would be like, what if your system is just a single object, but it's like a ball? Like a ball is really not like a point particle. It's made up of, trillions, quadrillions of atoms. And those atoms are all, they're moving around and they're doing their own thing. And when you push on the ball, you're not pushing on some abstract concept of ball, you're pushing on the atoms, and those atoms are pushing on the other atoms, and so on. So the question is how do we treat the work energy theorem in that case, where we realize that any given object is actually a composition of many, many, many other objects that we can't easily observe? The question you might ask is it true that the applied external force is always equally applied to all of the atoms? And the obvious answer should be no. So I'm just going to jot this down. So this is, imagine that you're picking up a ball. Is the externally applied force of you picking it up applied equally the same to all of the atoms? Equally applied force, sorry. Externally applied force. Wait a minute, I'm missing a word. In an object, is an externally applied force equally applied? There we go. That was the word I was missing. To all of the parts that make up the object. And as I said, the obvious answer is no, right? Like if you lift up a ball, all of the pieces of the ball move up together. So maybe you think, okay, well, in that case, they kind of are. But what if you flick the ball, right? If it's a rubber ball, some parts of the ball, the ball that you flick, the part that you flick will bend inward a little bit, but the rest of it will kind of just sit there. So there are cases where externally applied forces to objects are equally applied to all of the atoms in the object. And there are cases where they're not. And so the question is how does that affect what we mean when we say, or what we mean when we talk about the energy of a system? Because, if you just flick a ball, some of those atoms are going to get energy and not all of them will. So how do we actually describe that? So let's look at a quick example, a really, really simple example. So let's say that we have two objects, mass 1 and mass 2. They're not really joined by anything. We're just treating them as a single system. And let's say that we apply a force to the left object, right, to the left particle. Imagine that these are atoms that are loosely bound to each other. So that particle might move some distance, say delta x. And this particle with mass m2, might not move. So in this case, in this case, only mass 1 moves from that force. And so in particular, the center of mass position moves less than that one, moves less than x1. I mean, that should be fairly straightforward. If the center of mass was, say, here, and then this particle moves a little bit over to the right, now the center of mass will be, say, here, but it didn't move as far as m1 moved itself. And that's because m1, the center of mass is between m1 and m2. So this is just to say that the force that you apply to mass 1 causes less of a change in velocity on the center of mass than it causes a change in velocity on mass 1. So what does that mean for the kinetic energy of the system? What does that mean for this term, 1/2 mvcm squared? Well, we know that the velocity is smaller, but is the mass sufficiently large that it like compensates and balances out? Well, we can check. So the change in kinetic energy of the system due to this force that we're applying here would be 1/2 m1 plus m2. That's the total mass. It's the capital M here. By the way, we're assuming it was at rest to begin with, times VCM squared. And so now we have to go and think about this a little bit. So we would have to do some algebra. We'd have to figure out what is the center of mass velocity? How does it relate to the velocity of m1? So remember that VCM is capital F, it's d by dt of xcm, and then you could distribute that across. And in particular, because only mass 1 is moving, the only contribution to VCM, that's the point that we're going to get at. This is the kinetic energy of the whole system. So VCM is really, and you can work this out for yourself, prove this to yourself. This would actually work out to be m1 divided by m1 plus m2 times v1, where v1 is the mass of, or it's the speed of mass 1. So plugging that in, and by the way, we get that just from working out the formula for what xcm is and taking the derivative, and then setting that the speed of mass 2 is 0. So what we get is we get that 1/2 m1 plus m2 times m1 divided by m1 plus m2 v2 squared. We can rearrange and distribute, and we get that this is m1 divided by m1 plus m2 times 1/2 m1 v1 squared. Now, if you look at this term, that is the kinetic energy that you would expect of just mass 1. So this is a factor times m1, or times the kinetic energy, the change in kinetic energy of mass 1. And if you look at this factor, m1 is smaller than m1 plus m2. So this is to say that the change in kinetic energy of the system, measured from how the total mass of the system and how the center of mass velocity of the system changes, is smaller than the kinetic energy of the individual particle, which seems baffling. How could it be that the change in kinetic energy of a system is less than the change in kinetic energy of just a single part? Is that supposed to be v1 in the first equation? Sorry. Yeah. So how could that be possible? How could it be that the system gains less kinetic energy than the change in kinetic energy of just a single part? So the one way to imagine this is that from the perspective of just the system, imagining that we don't know what's going on inside the system, it's just the system, the center of mass of that system doesn't move very far. And so even though the force is the same, the center of mass doesn't move as far, so there's less work done on it. And so we would expect that the change in kinetic energy would be less because you have the same external force, but less distance traveled by the center of mass, and so you would have less change in kinetic energy. But that still doesn't explain how a single force can transfer different amounts of energy depending on the perspective that you view it from, right? Because you have a single force, and so if you view it from the perspective of the kinetic energy of this one particle plus the kinetic energy of the second particle, you would get one answer for the change in kinetic energy. But if you view it as just a black box, you have a force applied to a system, you would get a different amount of kinetic energy. And so that that seems very strange. And we're going to actually explain how this can happen. And it turns out we're not missing a whole lot, or no, how do I want to phrase this? It turns out that we were we were not accounting for something. So let me give an example. So another example would be, imagine you have a force that pushes on both M1 and M2. But in opposite directions. And it pushes on them precisely the right amount so that so that the center of mass doesn't move. Precisely the right amount. So the picture here would be, you're pushing on this one maybe a little bit harder than you're pushing on this one. And so M1 doesn't move as far as M2, but the center of mass is closer to M1. So the whole thing just kind of remains in the same place, the center of mass. So in that case, we know that the kinetic energy, the change in kinetic energy of the system is 0. And the reason we know that's true is because the center of mass doesn't have any velocity, right? It started off at velocity 0, it ended at velocity 0 because we decided that the center of mass position is fixed. And so the kinetic energy of the system's kinetic energy is 0. But clearly, in this case, you have M1 moving from left to right and M2 moving from right to left. Clearly, there is some energy there. The forces definitely did work. So the question is, where did that work go? So the place where it went, what we call this magical, mystical place where this work mysteriously vanishes to, it's not actually mysterious. It goes to a place that we call internal energy. So when we refer to mechanical energy in some system or in some situation, right, we refer to the mechanical energy of the objects that we can view and measure. So that is to say, the kinetic and potential energies, remember, mechanical energy is kinetic plus potential. Potential energies associated with individual objects in a system. Those are what we call mechanical energy. So the energy associated with motion, so there's kind of two layers of systems here, right? So the way to think about this is, let's say that you have a system, a large system. Is spring energy not involved in mechanics? Potential energy is a type of spring energy, or spring energy is a type of potential energy. Remember that. So like, let's say my system is the pen and the phone, right? So we would talk about the mechanical energy of this system by looking at, how is this phone moving? How is this pen moving? How are these related? Like, where are these in space? Maybe there's a spring between them, whatever. And so then the question is we can talk about the mechanical energy of those systems, but what we're not talking about is we're not talking about the individual motion of atoms in this phone. We kind of ignore those when we talk about mechanical energy, right? Mechanical energy is just referring to the objects in a large system, not about the particles in an object. So the energy associated with motion, with the motion and position / position. Remember, any energy associated with position is really a potential energy. The energy associated with the motion and position of particles in an object is called internal energy. So Are the objects themselves not systems? So they are. But the reason why we call it internal, the reason why we kind of just lump it all into internal energy is because, yeah. So you're right. This phone is really just a system of like trillions of atoms, right? Or quadrillions or quintillions, whatever. But the point is we kind of abstract that away because we have no way of zooming in and looking at the individual motion and the individual positions of each of these atoms. Like it's just not something that we can feasibly do. So what we do is we chunk the energies into different types. Energies that we can easily measure as mechanical and potential energies, and then energies that we can't easily measure as kinetic and as kinetic and potential energies. And so that's the point. So the point is if you wish to view the internal energy really as just mechanical energy, it's just mechanical energy of particles, it gets very complicated very quickly. There's a lot of particles involved. So in the example that I gave, here there's only two. So it was sensible to just say, okay, well, we could actually compute the mechanical energy of the system. We could compute the mechanical energy of the system by just adding up the mechanical energies of each of the particles. And so the reason why we got a different answer when we looked at the mechanical energy or the kinetic energy of the system as a whole, as opposed to the mechanical energy of just the individual parts added together, is because this system was kind of ambiguous, right? On one level, you could just view it as just a system, and then we just imagine all of the energies internal to the system are black box. We don't understand them. We just treat it all as internal energy. The other option was to compute all of them. And so, of course, they're not going to agree. From one perspective, all of that extra motion internal to the system is just internal energy. And so you'd get a different answer if you only considered the kinetic energy of the system as a whole compared to the total kinetic energy of each of the constituent parts. So the reason why we make this distinction really is because generally the internal energy, and in this case, by the way, this is not the case, but for more complicated systems like a phone with trillions of atoms, generally the internal energy is not directly measurable. Like you cannot, there's no way that you can zoom in on a phone enough that you can figure out the position and velocity. In fact, this is actually like fundamentally impossible, but even if it wasn't, it would be very impractical to try to add up the kinetic energy of each individual atom and the potential energy of each individual atom. It'd just be infeasible when we could just like we know that they're going to behave in a certain way, like we can approximate their behavior and get an answer, and by the law of large numbers, that answer will be close enough to exact. So this is all to say, given an object, we split up the total energy associated with motion. We split up we split up the total energy period of that object into energy associated with the motion of the object. That would be what we generally call mechanical kinetic energy or mechanical energy. And then the motion of the parts of the object that do not result in the object moving. So like, for example, in this phone, there's a trillion little atoms vibrating back and forth, right? But the object itself isn't moving. So what we do is we look at the energy of the phone. So if this phone's moving, now the phone itself as an object has motion, there's energy associated with that motion. But while it's moving, the atoms are still jiggling around inside of it, which also have energy. So we split up those two energies, we chunk them. We say that there's the mechanical kinetic energy. This is the energy just associated with the motion of the center of mass of the system. And then there's the kinetic energy associated with the individual motions of all the little constituent parts. So what we do is we split the total energy or the total kinetic energy of the system. So the mistake that we made was that this isn't really quite right, because this is only, erase William, this is only the energy of the system as a whole, not the energy of the little bitty internal parts, right? So what we really should write is we should really write that the external work done on a system is equal to the change in the mechanical kinetic energy. This is the kinetic energy on a macroscopic scale, plus the change in the kinetic energy of the internal itty bitty bits. And so this is how we can chunk objects into their macroscopic motion and their internal motion. And then we can separate them. Like this is something that we can easily compute. We measure the velocity, we measure the mass, and so on. This is something that's not easy to compute, but we can, in fact, measure it a different way. So the internal kinetic energy can be determined another way. So the way that we did do it, wait. Well, okay, so in principle, this is how you would have to do it if you couldn't generalize, which is what we'll talk about in a minute. So the way that we would do this is we would work in the center of mass frame, and this is where I promised why it was relevant. We would work in the center of mass reference frame, and compute the kinetic energy of each particle. So the reason why we want to work in the center of mass frame is because from the center of mass frame, the total energy is the internal energy, right? Because in the center of mass frame, the mechanical energy, if I'm moving along with this phone, from my perspective, the phone's not moving. And so this term, the mechanical kinetic energy, is 0. It's just not changing. Whereas and so all I have to do is just find the total energy, just add up the velocities of each of the, or add up the kinetic energy of each of the particles in that reference frame. And those will be the motions of those particles that don't cause overall motion. Because if you think about it, when the phone's moving, all of the particles are moving back and forth, but they're more often moving to the right than they are moving left, right? And the reason for that is because on average, if the whole system is moving, then on average, each of the particles is also moving, even if they're jiggling around a little bit themselves. It'd be like staggered to the right. They're still moving to the right. They're just still jiggling around on their own. And so that's why the center of mass frame is useful. You can use it to compute the internal kinetic energy of some complicated system. So in this case, what we would want to do if we wanted to find the internal kinetic energy is we would work in the center of mass frame and then figure out what are the velocities of the two masses. And we would find that they both have some contribution because the center of mass frame is moving. M1 would be moving slower in the center of mass frame than it was in the rest frame, and M2 would be moving faster and to the left in the center of mass frame. Sorry, it would also be moving. Yeah, it'd be moving to the left. And so you could figure that out by using this notion of relative velocity. All you do is you set your how do I want to phrase this? You can find the velocity in a different frame by just adding or subtracting. Remember, if I'm going 5 meters per second north and somebody else is going 10 meters per second north relative to me, then they're going 15 meters per second north relative to someone who's stationary. It's just this whole, and then you could reverse it to get to go back and forth. And so you can use addition and subtraction to figure out relative velocities. And so that's what you would do if you wanted to actually make this addition add up. So the end result of that would be that the kinetic energy that you computed, the total kinetic energy of the system, would be the kinetic energy of the system, which we computed here, plus the kinetic energy of the objects in the center of mass frame. And that would give you the kinetic energy of just mass 1. I'm not going to go over this in detail. I'm not going to go over the calculation in detail. It's laid out in the LibreText, and it would take a very long time to go over. But I just wanted to get the idea across of how this actually works out. You can split up a problem. We have to figure out relative velocity at an angle. You might have to. I did this in a one-dimensional case because it's easier in that case. But in general, you have a whole bunch of particles moving in every which way. You might have to figure out relative velocity. And in that case, it involves vector addition. So just as a quick aside, this separation between mechanical and internal energies doesn't just apply to kinetic energies. For example, let's we know that there are bonds between atoms in an object, right? So not only are there just a trillion atoms zooming about freely, those atoms are connected by basically little springs to other atoms. And so there's also internal potential energies, which are, because they're jiggling about, they're bouncing back and forth between 2 points. And so those potential energies are also internal, and so those would also not be measurable. And if we wanted to find the internal potential energies, we would again have to work in the center of mass frame of the system. And then from there, we could go and measure the potential energies, and that would be that would give us the total internal potential energy. Whereas external to the object potential energy would be like if the phone is on a spring, right? If the phone's on a spring, then it has some mechanical potential energy. So this leads really nicely into this notion of thermal energy, which we briefly touched on, but we never actually really well explained. So thermal energy, as you may have figured out by now, just from the way I've been talking about internal energy, thermal energy is an internal energy. You guys probably have this concept that higher temperature things are a bunch of atoms jiggling about faster than lower temperature things. Maybe you don't, maybe not. But the reason why we can tell this just from the get-go is that thermal energy is not a result of any measurable motion or change in position, right? If I heat up this phone, however which way, maybe by friction or something, like let's say my phone is stationary, right? I start rubbing my phone really fast to get it hotter. So the phone isn't moving. The phone isn't changing its speed, yet somehow its energy is increasing. And that energy, therefore, has to be associated with the internal motion, or the motion internal to the system, has to be associated with, you know, the atoms and the molecules in the phone start moving faster. Just as an additional point, thermal energy, the difference between all internal energies and thermal energy is that thermal energies have to be associated with random motion inside the object. That's just a quick caveat. It's not a thermal energy if it's not random. You can have internal energies that are not random, but are still internal. So if the phone itself is moving fast, that wouldn't affect the thermal energy. Yeah, like, I mean, like maybe there's air resistance, but if I like chuck my phone, like the phone's not heating up. It might heat up because if there was like air friction or something, but if I chuck my phone and in a vacuum, the thermal energy of the system's not going to change. It's the mechanical energy of the system that's changing, right? That's a good observation. Right, so thermal energy is just a form of internal energy. And so then the question is if you can't measure the internal energy of a phone, because you can't zoom in and look at all of the atoms, what do you do? What you can do is you can measure the temperature. And this is why it's called thermal energy. So it turns out that temperature, and you'll learn about this in 9b, temperature is directly related to roughly the average speed of the object, or of the particles or of the atoms in your object. And so as long as you know that there are a lot of particles and they're moving randomly, then on average, you could just figure out the total energy, total internal energy, by measuring the average speed. You know how much that, you know what the mass of the objects are, you know what the mass of the atoms are. If you can find the average speed, then you can just find the total internal energy. And because there's so many, that average will basically be exactly what it actually is. So that's what temperature is good for. And that's why it's called thermal energy. Now, I'm not going to talk in any more detail about this because this is basically the subject of the first half of 9b. But it is interesting that there's a relationship between temperature, or rather, it's not that there's a relationship, that temperature is a measure of the average speed of the atoms in your object. So just as a quick reminder, from earlier today, when external forces, or actually, let me write this down, just that way then you have it in your notes if you don't already. So external forces contribute to internal energy. When the force doesn't act equally on every part. And the example that we saw was pushing just one part of a two-part system. Thermal energy, so there's a formula for thermal energy in terms of temperature, but you'll learn that in 9b. So in the example of the two masses, if you just push on one of them and you don't push on the other, that contributes to the internal energy of the system. If you had pushed on them both equally, then the internal energy of the system would have been 0. You wouldn't have changed it. When the accelerations that you get from the forces that are applied are the same on every particle, then the entire center of mass accelerates, and there's no relative motion relative to the center of mass. So a good example of this would be kinetic friction, right? So when you have two things rubbing against each other, causing kinetic friction, or rather, and so there is kinetic friction between them, what you're really doing is the parts of, let's say my phone, right? The part of my phone that's touching my hand, like the atoms in my phone that are close to the atoms in my hand, those are being shoved around by the atoms in my hand, right? Because they're bumping into each other and they're pushing against each other. But the atoms on the top of my phone they're not being pushed around by anything. They're just doing their own thing. And so the kinetic friction acts non-uniformly on the part that acts non-uniformly on the atoms in an object. It acts in particular on the atoms that are at the interface. And so there's an acceleration that the kinetic force applies to, like, the little atoms at the interface that it doesn't apply to the atoms not at the interface. And hence, because external forces contribute to internal energy when the force does not act equally on every part, in this case, there is an acceleration on the atoms at the interface, but there isn't an acceleration on the atoms away from the interface. And so that's why kinetic friction contributes to internal energy. In particular, it contributes to thermal energy. So hopefully, and I know that there was a lot of words here, but this was more of just an explanation than it was like teaching how to calculate something. But the idea is, hopefully it kind of makes sense now what non-conservative forces are. Non-conservative forces are just forces that don't act equally on every object, or don't act equally on every particle in an object. Friction is a non-conservative force, generally, kinetic friction. And in a lot of cases, we just treat our objects as rigid bodies, in which case the whole object moves together. So for example, for a spring, because if we treat the mass that is attached to the spring as a rigid body, if you push on one, it pushes on all of the other ones equally. And so they all accelerate together, so there is no change in thermal energy or internal energy. But in reality, once the spring starts pushing your block, it pushes into your block a little bit. It deforms the block a little bit. It pushes a little bit harder on the edge closest to it than it does on the edge furthest from it. So you get a little tiny bit of heating. So in the real world, there aren't really any non-conservative forces, with the exception, by the way, of the truly fundamental forces. These are things like gravity and electromagnetism and so on. Right, so that's a lot, but hopefully you guys at least now have a slightly better understanding of what internal energy is and where thermal energy comes from and why it comes from non-conservative forces. I just really want to briefly go over the notion of kinetic energy being different in two different, I want to briefly go over the notion of how kinetic energy can be non-uniformly distributed in a system. So let's look at that really quick. It's just going to be a quick example, and then we'll move on to a separate subject. We're going to way run out of time. Okay, so in fact, I'm actually not going to go over this example. It's not like question on gravity, can certain parts of the same system be affected differently? No. So it turns, well, okay, yes, but also no. And we can talk about that after lecture. So the example I was going to go over, it's kind of informative in that it basically lets you see how even if two objects have the same momentum, they can have different kinetic energy. But it's just kind of a useful result, or it's just kind of a decent example. So if you do want to take a look at it, go look at the lecture notes. Again, this is also in the LibreText, so take a look at it there. But I'm going to skip over it because I have actual useful material to get to. So I promised that we would actually get to using momentum conservation. So let's actually do that. Let's talk about collisions. Right. So in collisions, the nature of the force between the objects doesn't affect momentum conservation, but it does affect the change in thermal energy, right? So like, remember that so long as there are no external forces on a system of say two objects, then the momentum is conserved regardless. So like, for example, I want to take two things that I can throw at each other. Okay, here we go. This is the cap of a Cholula bottle. This is the cap of a larger Cholula bottle. Two caps, right? So when these two things collide, there's going to be some complicated force that causes them to bounce off, right? Maybe there's like some springiness to them. Maybe there's like some electrostatic repulsion from the electrons, whatever. But they collide and somehow they bounce off, right? But the point is if we treat the system as just these two objects, it's just the two caps, then any force that's between them, that's an internal force. It's not external to the system. And so momentum will be conserved regardless. However, the type of force that occurs between them might affect energy conservation, because we know that even though momentum doesn't, or impulse doesn't have a third law equivalent, or rather impulse does have a third law equivalent, hence internal forces don't affect momentum conservation, work does not have a third law equivalent, which means that internal forces can affect how the energy is, which means that internal forces can affect how kinetic energy is distributed. Internal forces can, for example, let's say that these two caps, they came together, they rubbed a lot somehow, and then they split off, right? In that case, the kinetic energy will be less going out than it was coming in, because there will have been some internal kinetic friction forces that convert some of their kinetic energy into thermal energy. So the type of force does affect what happens in a collision, even though it does not affect momentum conservation. In particular, if the force, scroll Willie, if the collision force, and by the way, a collision can refer to a lot of things. It can refer to two things sliding together. It can refer to two things bouncing off a spring, whatever. If the collision force is non-conservative, I'm abbreviating non-conservative, even though momentum is still conserved, we can still have, so if the force is non-conservative, we can have a change in thermal energy that's not zero. Which is to say, if the internal forces are non-conservative, then you can lose energy to thermal energy. If the collision force is springy, the collision force is springy, and I say springy in a very vague sense, meaning conservative. Like, for example, let's say that you had two blocks coming in and then they bounce off a spring. That would be an example of conservative collision, because the only forces present during that interaction are conservative forces. So if the collision force is springy, i.e. the force is conservative, then we call the collision elastic. So that's a name we give it. And truly, in a lot of cases like that happen on Earth, what we might call an elastic collision isn't really an elastic collision. Like if you have two billiard balls and they bounce off each other, we might call that an elastic collision because it's very nearly perfectly elastic. But in reality, there's always a little bit of energy loss somewhere. There's always a little bit of non-conservativeness to the force. And so it's not actually an elastic collision, it's just close enough. So we might call it an elastic collision. If the collision is frictional in nature, or just non-conservative, so the example here would be like you have one block, you have a book that's stationary and then another book that comes in and slides on top of each other and then they move together. That would be an example of a frictional collision. So if the collision is frictional in nature, like the book sliding, the force is non-conservative, And we call those, not those collisions that involve non-conservative forces, inelastic collisions. So there's basically two classes of collisions. There's elastic collisions, which involve only conservative forces internal to the system. And there are inelastic collisions, which involve forces only, or which involve at least one non-conservative force internal to the system. And by the way, when we're talking about collisions in general, we always neglect external forces. Like, we don't worry about gravity, we're just worrying about two things colliding and then something happening. So I think that that's actually probably a good stopping point. We will pick up next time talking about elastic collisions, and then we'll move on to inelastic collisions. Now, we are, by the way, a bit behind, which is unfortunate, but that just means I'll just push the material back. And so either we catch up or we don't, and either we will get to as far as I would have liked to by the end of the quarter, or we don't, and that's just okay. Right, so I'm going to end the recording here.